Hey, welcome back. My name's Joel Duff, and you've just opened the video for part 10 of the Dead Sea Chronicles. The Dead Sea Chronicles, yes, we're exploring the Dead Sea Basin's geological history. And through this series, we've been uncovering evidence of multiple desiccation events, significant fluctuations in the Dead Sea levels, the lake levels. We've looked at what appears to be a history of hundreds of thousands, if not millions of years to develop this fascinating geological feature. These findings derive from sediment cores, different dating methods. They all paint a really complex picture of this region's climatic and hydrological past. And so, as we've seen previously, this represents a really significant challenge to any advocate of what's called young Earth creationism. The idea that all Earth's history can be compacted into just 6,000 years, and in this case, into just 4,350 years, or the time since a global catastrophe. So, how have young Earth creationists responded to the things that I've mentioned in the previous 9 episodes, or in the literature before I started this particular series? When young Earth creationists do mention the Dead Sea in their literature, the treatment is very superficial, only representing superficial features of the modern Dead Sea without addressing its origins, without addressing the fact that there's piles and piles and piles of sediments right below the feet of these individuals walking on this fairly recently deposited salts that you can see along the edge of the Dead Sea. One would think that a place which Scripture provides us with eyewitness testimony would be exactly where creationists would go first to try to provide evidence for recent origins. Right? They want to try to show that the Earth is only 6,000 years old and that all the features of the Earth were created by a global flood. You'd think you would go right to the underneath the feet of those who walk there in biblical times to try to understand how that could have been formed in just 4,350 years. And yet, this particular location seems to be almost universally ignored in the young Earth creationist literature. And what this particular episode is going to be all about is the question of where did the salt come from? I should have just labeled it that. Where did the salt come from? Enormous amounts of salt. We're going to calculate how long it would take to deposit that salt. Here's just some recent salt right along the shore. You can see the crust at the top there, but you see the layers underneath representing prior years, actually probably decades at least, of sediment deposition along with salt deposition. But if you've watched any previous parts of this episode, you know that deep below this very point right here, there are thousands and thousands and thousands and thousands of feet of similar sediments that need to be explained by anybody interested in the origins of geological features on Earth. Whoa. I got to slow down. Before I go off on too many tangents here, let me bring myself back and give you a brief summary of what I'm going to cover in this video. We're going to be calculating time. We're going to be calculating the Dead Sea salt deposits, how long it would take to evaporate as much salt as there is underneath the Dead Sea. So I have to remind you, well, how much salt there is under the Dead Sea, and that's going to require doing a brief survey again of the Dead Sea Basin's geological history. All right, then we'll talk a little bit about the evidence for desiccation events. You're going to see that again in this video, even though I've covered it in the past. And we're also going to, of course, use this as a challenge to young Earth creationism. So that's going to be sprinkled throughout this particular video. But along the way, I hope you learned something about, halite and gypsum and desiccation rates and past climates and environments and so forth. A little bit of all that stuff coming right up in this particular video. All right, really brief reminder of the location we're talking about, because we're talking about the Dead Sea, which is a lake that's at the bottom of the Dead Sea Basin or the Jordan Valley. That Jordan Valley is the result of two continents that are sliding past each other and kind of slightly pulling apart, causing a drop down basin in which the earth is literally falling down between the two plates. And as it does so, it creates this basin in which, water and sediments run into it and they pile up in there. And it's that pile of sediments that we're most concerned about. This is a cross-section of that basin showing you have Jerusalem's over here on the left-hand side, and we have Jordan over here on the east side. And so we have Miocene sediments, which are rocks that used to be part of the continent that was running all the way across this region before it cracked and separated. And once it separated and all this Miocene, Mesozoic, and Paleozoic rock fell down and continued to fall down farther down into the crust, above that is deposited sediments that are very recent, very young sediments. And at the bottom of all those sediments, the young sediments that fill in the basin, are Pliocene sediments, which are predominantly salt. So that's going to be the stuff we're really concerned about, like where does it come from? Now, I'm going to talk a lot about 2,000 feet of nearly all halite, which is just rock salt. Right? There's a little bit of other stuff in there too, but it's primarily just salt. And that's the white stuff you see here. And then you have a lot of other deposits on that, which include much more salt, but in thinner layers. All right, so the question for this video is, where did that salt come from? How did it get there? Because there aren't salt layers in the Miocene, Mesozoic, and Paleozoic to any significant extent. All of a sudden, there's this really thick layer of salt. The question is, where did it come from? What's the origin of that particular salt? All right, so here's a core section we talked about in 2 episodes ago. We talked about the Dead Sea drilling project, taking cores down through the bottom of the Dead Sea, which is taking little snapshots, right, of time, because those sediments have been piling up. And you see all kinds of different forms of sediments there that represent different climatic conditions. When the lake was high and not as salty, then you had other sediments, and maybe you had more organic material, things actually living inside the lake and therefore dying and falling to the bottom. So you had more organic stuff. You have times when it was more salty than it is today, and that's where you would get thick halite deposits, salt. You have aragonite and detritus couplets, which represent sort of annual fluctuations between rainy season and dry seasons. You have gypsum, and we're going to talk a little bit about gypsum in this particular talk as well. That tends to precipitate out at slightly less saline conditions than is found today, which halite is what's precipitating out of the lake presently. And so this is a core which represents sort of a historical progression, right? It's a trip through time. And we're going way back to the bottom of this core and looking at massive amounts of salt and asking how that salt got deposited there. So what we're interested in doing in this video is we're asking the question, what in the world does a young Earth creationist do with all this salt? How do they explain the origins of that? So we have to think about what a possible hypothesis is for a young Earth creationist. Somebody who believes the world is only 6,000 years old. Where did that salt form? It wasn't just formed in the original creation, because the salt is sitting on top of 20,000 feet of sediments filled with fossils that they claim were deposited by a global flood just 4,350 years ago. So the salt is sitting on top of that. So it seems to be of very recent origin. And so that leads us to this possible assumption, right? It was post-flood, and there was a huge lake that must have filled the Dead Sea Basin. After the flood, right, the waters covered the earth, and so therefore there's water that would have been left over in this basin as a very large lake. And so one hypothesis, which I have been has been suggested to me many times since I started this series, is that Noah's flood simply left a large lake that was salty, right? Another assumption would be the post-flood Dead Sea water was like salty, about as salty as the ocean is, because after all, the world was covered with this ocean water at one point. So it would have started out salty. I don't think it would have been as salty as it is today. And besides, many people believe that the flood was sort of semi-salty, right? Kind of brackish water, not as salty as the ocean. But let's grant the young Earth creationists that it would have started with a giant lake of salt water. What we're going to do throughout this particular video is I'm going to give the most generous assumptions, right? We're going to look at the most generous calculations that we give the young Earth creationists the best chance to possibly explain the origins of this salt. So what we're going to start with is we're going to ask the question, hey, if you started with a giant lake of salt water and then allowed it to completely evaporate, how much salt would be left? How much salt would be left? Could it explain the amount of salt that we see in the sediments below the Dead Sea? Because that's one of the primary hypotheses that I think that young Earth creationists would present to explain the salt. So we need to know, to do that calculation, well, how much salt is in seawater, right? Average seawater salinity is 35 parts per thousand, or 3.5% by weight. This means there's 35 grams of dissolved salts per kilogram of seawater. I'm going to throw lots of numbers at you. You can go to my blog post in which all this is going to be outlined, and some of the formulas are going to be in there as well. But I tried to simplify it for this particular video. So what's the composition of those dissolved salts? Right? Actually, with the 35 parts per thousand, we're talking about the saltiness of the water. We're not talking about other dissolved things in there like other sediments, right? So like clay particles and so forth, which are going to fall out and form layers of clastic sediments at the bottom of the Dead Sea. We're talking about the things that are going to precipitate into different compounds and fall out. Most of those dissolved salts are going to be sodium and chloride. All right, 85% of the salinity is from sodium chloride, but there's also magnesium, calcium, potassium, sulfate, right? Those can all combine in different ways with sodium and chloride as well to form other compounds. And that's why you get not just salt deposits, but you get gypsum deposits, and you get aragonite, and you get some of these other things that form from different combinations, and they precipitate at different salinity levels, all right? Also slightly different temperatures and so forth. So that represents different environmental conditions of the lake, what kind of thing is precipitating out. So our goal is to estimate the thickness of a salt layer resulting from the complete evaporation of all the seawater that filled the Dead Sea Basin. So we're saying, like, let's grant the young Earth creationists that the entire basin was completely full of water until it spilled over the edge, all right? And so in order to determine that, we have to have some idea, well, what is the total volume of the Dead Sea Basin? And again, we're going to give them the benefit of the doubt in terms of we're going to give them the largest space we can really give them, which is like the full depth of the Dead Sea Basin, even though in the past it probably wasn't as deep, because remember, it's constantly falling and it's getting deeper all the time. But let's assume that right after the flood, or at the end of the global flood, the basin was already there. I think that's problematic, but well, let's just give them that the basin is already present. So I've turned it into a rhombic prism, all right? And we'll say 80 kilometers length, 15 kilometers wide, and a little over half a kilometer deep. All right, take that all together, and that it represents the total volume of water that would fit in that entire basin. Again, I'm overestimating here. That's actually a little bit larger than it is presently, but I want to give the young Earth creationist the most possible room to be able to explain the salt layers. So we're being favorable to the young Earth timeline. All right, so we've got our volume. We've got salt water. We know how much salt there is in that volume. Well, we can calculate that now, right? We got 720 cubic kilometers of water, right? The salinity is 3.5, mostly sodium chloride. So the total seawater mass is 738 trillion kilograms. Total salt mass is 25.83 trillion kilograms. All right, 25 trillion kilograms sounds like a whole lot. I mean, the number is billions. I mean, trillions are just unimaginable numbers. And so you would say, like, okay, so you got that much salt, right? If everything dried, if all the water evaporate, you'd have 25.83 trillion kilograms of salt. What would that look like? Like, how much, mass would that be? How much of a layer would that be laying there at the bottom of that basin? Well, we also need to figure out the density of halite, because halite is rock salt. So first, when you precipitate salt and you get it into, little crustules, all right, crustules, that's not really a term, frustules, they're not going to be very compact. And then as you eventually have more and more and more salt and you compact it together, it'll form a crystal lattice that becomes like large salt crystals, in which case it's much, much more dense than it was before. And so the density of like rock salt is 2,170 kilograms per meter cubed. So the total volume of salt precipitated is 11.9 billion meters. And we had a surface area of the basin. So the basin top, the amount of surface area there was of this lake was 1,200 square kilometers. All right, 1,200 square kilometers. And so if we were to say like, okay, if you laid out 11.9 billion cubic meters onto 1,200 square kilometers, you'd have salt that was 10 meters thick. That would be 33 feet. All right. Dry up that entire basin, and you're going to end up with 33 feet of pure salt. Now, this is a super rough, unrealistic estimate. There's a whole bunch of other things wrong with it. So I do want to cover some of the other things that are happening here. Right? You're not going to just get straight up like salt is precipitating the entire time that it's drying down. Salt precipitates as the water levels drop, right? As the water levels drop, it means water's leaving and the water's getting more salty. At 35 parts per million, salt isn't precipitating in salt water and forming salt crystals that are falling to the bottom of the ocean, because 3.5 parts per million is not, 3.5 parts per thousand it's not, enough salt in order for precipitation to occur. The salt will begin to precipitate only after the water reaches a certain salinity, right? A much higher salinity, like the salinity that it is today. The other thing is, as the lake shrinks, it's not a rhombic, right, prism, right? It's a valley. And therefore, the lake had a much larger surface area to start with, in which case evaporation can occur quite quickly. But as the lake shrinks, the amount of surface area is reduced. When the surface area is reduced, evaporation starts to slow down, right? Because there's less surface area to evaporate from. And so you only have about half the basin at some point when the actual salt begins to start to crystallize and fall out, right? You should precipitate. And so, and even that is a very, probably an overestimate. It's probably even less of a basin before that happens. And so the localized salt, where the salt actually precipitates and falls, is going to be in like half of the basin area. So now, since we're laying the salt down in half the amount of surface area, we're going to have 66 feet of salt that's deposited. Right? 66 feet of salt deposit. So all you need to remember, out of all those things I said, if that just sounded like a bunch of mush, if you can believe that 66 feet of salt would be deposited if you just evaporated all the water, you're going to have 66 feet. But now I'm going to tell you, we've got a solid 2,000 feet, 600 meters of salt lying way down there underneath the Dead Sea sediments, right? That's 2,000 feet. How long would it take to get how many times would you have to dry down the entire basin in order to get 2,000 feet? That would be about 30 complete evaporation cycles, which means you'd have to fill up the Dead Sea Basin with seawater 30 times, dry it all the way down, right, between each one of those 30 fills, and you'd have about 2,000 feet of salt deposited from that. But you got to remember, there's another 15,000 feet of evaporites, including thousands of feet of salt, just in thinner layers. But if you add it all up, you still got a couple thousand additional layers of salt on top of that thick salt layer, right? And a bunch of other sediments too. All right, so we've got this giant block of salt that also then has to migrate up and get squeezed out between the, up through those other layers above it to form Mount Sedum. So you have to go back to watch that previous episode about Mount Sedum to see that. So the basic message here, it takes a lot of evaporation in order to generate that much salt, the amount of salt that we actually observe, right? The amount of salt that's actually there, the fact of the salt, right? There is that much salt that exists underneath the Dead Sea. And so 30 evaporation cycles have to occur. Well, 30 evaporation cycles, each evaporation cycle must take some time, right? So you have to do 30 times that amount of time to find out how much time it would take to get that much salt precipitated out of water. And I can tell you it's going to be a pretty long time, but let's do the calculations. All right, let's figure it out. So how much time does it require to completely evaporate the Dead Sea Basin? I'm sitting right here in the bottom of the Death Valley, all right, in California. So Death Valley, similar to the Dead Sea Basin, It's a pull-apart basin. The basin's falling down. It's below sea level. And at one time, there was a large lake, right, in Death Valley. There are places where you can see shorelines, right, hundreds of feet above the bottom of the valley, where the previous lakeshore was, right? Much like there is in the Jordan Valley. We talked about how there's shorelines way up there, hundreds and hundreds of feet above the current lake. And so what happened in Death Valley is that there was water in this basin, and it all evaporated completely, right? Leaving a whole bunch of salt and gypsum. And I'm just in these boulders of halite rocks here. And there's hundreds and hundreds of feet of salt layers below where I am sitting. So this is the result of completely drying up that Dead Sea Basin. And the question is, how long would that take? When did the Death Valley have a lake, and how long did it take for it to evaporate? Well, let's find out. But for the Dead Sea. So let's, what are our initial assumptions, and what are the ideal conditions? When I say ideal conditions, I mean, like, how can we make this happen as fast as possible? Right? Which is what I think the young Earth creationists are going to need, right? They don't have much time. They only have a couple hundred years between the flood and when Abraham and Lot are looking down into a valley and they don't see a giant lake, right? They see there's a salt lake at the bottom, right? But they see a valley that has agriculture going on, right? So therefore, there's only a couple hundred years available. So if there was a giant lake there at the end of the flood, it had to have completely dried down to a very small lake left in the space of only a couple hundred years. So can we do it? Can we dry up an entire lake in a couple hundred years? That's what we want to find out first, before we find out how many times you'd have to dry it up to fill it with that much salt. So let's do a simple calculation under ideal conditions. Let's assume the Dead Sea Basin was, as I said before, this 80 by 15 by 600 meter depth, right? And let's say the total volume then is 720 billion cubic meters. So we start with that same amount of seawater. And here's another really important assumption, right? Again, we're trying to like make this happen as fast as we can. We're going to say there's no new water input into the basin. Totally unrealistic, right? In other words, there's no Jordan River, and there's no rain in the area around it, which is collecting into this basin. We're going to say it's extremely dry, right? The environment, there's no rain happening here. And we just have a lake, and we're going to allow it to dry up. How long is it going to take? You want to take some guesses out there? In the chat, if you're in the live, like, you want to guess, like, how many years would it take just to dry that much water up? All right, let's do it. So again, here's our some more conditions. We have very low humidity. Let's say 5% humidity. And this means 5% humidity all year long. Again, completely unrealistic. Realistic on some days, but not every day. Right? As the water gets deeper and deeper, and as the water dries up and the lake gets lower and lower and lower, the humidity is going to rise inside that valley because there's a lot of vapors that's sort of trapped down there. As the humidity increases, it lowers the amount of evaporation, right? But we're assuming 5% humidity all the time. So evaporation is occurring, and also it's really hot. It's 100 degrees every day, like all the time, 100 degrees. Of course, it's not 100 degrees there all year round, but again, we're trying to make this happen as fast as possible to find out what the fastest rate at which this could occur. We got an evaporation given those conditions, of 10 to 15 millimeters per day. So the entire surface area, right, which we're assuming is 1,200 square kilometers, right, which is a huge surface area. That's going to evaporate 10 to 15 millimeters a day, which is 10 to 12 million cubic meters of water is evaporating. All right, now you put that all together, you do that calculation there, and what you figure out is that's going to be 100 to 165 years. 100 to 165 years. I think that's pretty impressive, actually, that within 100 years, you could take this humongous lake and you could just dry it all the way down to nothing. I mean, not even to like where the Dead Sea is today. I mean, dry it all out, like get rid of all the water. Of course, we're going to violate a bunch of these assumptions. And all the violations are going to make the time it takes to evaporate all the water longer. I can't think of anything to make it happen faster, right? Everything I'm going to mention here, which is more realistic, is going to make that time frame longer, right? Let's start out with as the water evaporates, right? You start out with just like regular seawater. As the water evaporates, the seawater becomes more saline, right? And when it gets up to 26% salt, right, it's going to reduce the amount of water that can evaporate, right? Because there's less water at the surface, right? There's more salt. And so evaporation slows down as the lake gets lower and lower and lower, or the volume gets reduced, right? So that right there is going to push it past 100 years. All right, when the water reaches saturation, that's when the salt begins to precipitate out. Once it begins to precipitate out, it doesn't get any more salty, right? But also the evaporation can't increase. It's going to stay right at that level. And then, of course, you got a shrinking water surface area. We're talking about 1,200 square kilometers, but that's at the beginning when you have the lake filling the basin, and really it's a valley, remember? So as a valley, you have a lot of surface area, but as the lake shrinks, there's less surface area. Less surface area means you slow the evaporation down. So you're not really getting rid of 10 to 15 millimeters per day. Oh, sorry, you probably are getting rid of 10 to 15 millimeters per day on the surface, but you don't have as much surface. So it's not going to be 12 to 18 million cubic meters of total water evaporating. It's going to be half of that at some point, and actually right now it's far less than that because of the size of the lake. All right, so when you factor in decreasing evaporation rates, complete evaporation is going to take several hundred years, not just 100 to 165, probably in the range of 300 to 400 years. And that assumes there's no water inflow. Okay, you don't have a Jordan River bringing in fresh water. You don't have any rainfall. You don't have any springs. There are lots of springs right now that feed the Dead Sea. Right? So for every bit of new water you bring in, you have to evaporate that as well. And so we're going to have to add that to the calculation. So even today, there's minimal water input. Right? We talked about in the second episode how there's not nearly as much water coming in the Jordan because people are sucking it out. They're sucking the Jordan dry because they're taking it out for agriculture and for, taking it over Jerusalem for drinking water. All right. The lake's only dropping like a meter per year, which is pretty impressive. But nonetheless, not nearly what it would be if there was less fresh water coming in. So if the basin started full, it would take, I would say, 400 years probably to reach today's lake level at the current conditions, which are very favorable to things drying up. So if in the past the climate was a little wetter, all right, there's more water input, that's going to slow the whole process of evaporation down, slow the process of salt deposition down, and therefore it's going to take even more than 400 years. And remember, young Earth crystals only have 400 years, right? The flood ends, there's a giant lake there. They need the lake to be gone between 4,350 years ago at the end of the flood and 4,100 or 4,000 years ago when Abraham and Lot are present. And then remember I had that episode where we talked about all the different cities that are, really old, at least 4,000 years old, if not really a whole lot older than that. But let's just say they're 4,000 years old. If they're 4,000 years old, they represent cities that are, 1,200 feet below sea level. So therefore, the lake was gone by that point. Now, as we mentioned a few minutes ago, right, to account for the really deep salt deposits, right, we're going to just keep talking about 2,000 feet of solid salt. We said the basin would have to fill up 30 times and dry down. Well, if it's going to fill up 30 times and you had absolutely optimal conditions, like no water input, 100 degrees, 5% humidity, and it only took 100 years to dry that amount of water down, it would take 30,000 years to evaporate the necessary salt water in order to get 2,000 feet of salt. 30,000 years. Under absolutely optimal conditions. Make it 400 or 500 years, and suddenly you're looking at over 100,000 years. But of course, the problems don't stop there for the young Earth creationist. The sedimentary record suggests that the events weren't sequential. All right. Rather, there was interruptions of long stands in which the lake was high, then the lake was lower, then the lake was high again. And when the lake was high, salt's not being deposited. Right? The salt's only going to be deposited when the lake is really dried up to a great extent and the salinity gets to a high level. All right, so we have to conclude the evaporative process might have taken significantly longer than 30,000 years. All right, we're talking about hundreds of thousands of years. All right, because it's intermittent. We're not going to have constant salt production every single day, every single hour. Even now, salt production only occurs during like one season, right? During the hot, dry season. I'll just put this slide up here because it's a summary of sort of what we just talked about with the conditions that would affect evaporation, what the most favorable conditions would be for that we've mentioned. And I think we talked about all these. Humidity, evaporative rate, yeah, increasing salinity and so forth. Okay, so now, the young Earth creationists might come back and say, but, okay, all right, so you only had one volume of salt from the original lake that was there after the flood. And yes, that only can make like 66 feet of salt, right? That doesn't come anywhere close to 2,000. However, we do know that there's a Jordan River, right? And the Jordan River is bringing in some salt. And there's springs that are bringing in some salt. And there are flash floods and rainfall events that create wadis that run periodically through the year and bring sediments into the Dead Sea, some of which, and some salts, right? And so salt has been continuously added to the Dead Sea for the last 4,350 years. And so maybe it's just constantly bringing in salt and new salt layers are being laid down. And so maybe that explains it. So let's figure out how much salt is added to the Dead Sea each year and see how much it would accumulate over 4,350 years. So the Jordan River, which is the primary source of new water that comes into the Dead Sea, all right, it really by a lot. All right. So we're just going to consider that. And then you can, like multiply that by a third in order to figure out how much more salt is added. So the Jordan River starts way up north at the base of Mount Hermon. All right, so a portion of the snow from Mount Hermon that's melting is coming down, traveling 156 miles before it gets to the Dead Sea. And historically, and I have to say historically because right now the flow is very low because, as I said, we're pulling a lot of it out. But, what would be typical before we dammed it up and sucked water out? 1.3 billion cubic meters of water per year. All right, so you've got 1.3 billion cubic kilometers a meter, and the total dissolved solids, all right, the total dissolved stuff that's in that brown water that comes down is 1 gram per liter. And out of that gram of liter is some salt, right? Let's just say, let's like think of it as like most of it's salt, all right? 1.3 billion cubic meters times 1 gram per liter is 1.3 million metric tons of dissolved salt per year. That sounds like a lot, right? 1.3 million metric tons of dissolved salts being added to the Dead Sea each year. So over 4,350 years, let's say it's just like that's been happening every single year. That's 5.66 trillion kilograms of total dissolved solids. Now that does include clays and sand. I mean, like it includes in detritus and like organic material and other stuff too. But let's just say it's mostly salt, even though it's not. Because remember, we're trying to help the young Earth creationists come up with as much salt as possible in order to try to explain the vast deposits of salt under the Dead Sea. All right, so even if all of it was salt, that would still only be 18% of the salt that would precipitate from a single seawater filling of the basin. So if you filled up the entire basin with seawater, that amount of salt that you'd bring in over 4,000 years would still only be 18% of that salt. So it doesn't contribute a whole lot, right? 18% would be, go through the calculations here. I'm trying to speed up because we have a lot to cover. That would be 1.8 meters or 6 feet of halite across 1,200 square kilometers. But of course, we're saying that the footprint is reduced because, most of the time, this history of the lake, it's a smaller lake. And so therefore, let's say we're adding 12 feet to the 66 feet, right? We had 66 feet. Now we're adding 12 feet over the 4,350 years that have passed. So now we've got 78 feet of salt. 78 feet of salt. We're nowhere close to the 2,000. All right, so a hypothetical single evaporation event, which is the hypothesis that has been presented to me, right? Hey, the salt came from the salt water that was left over from the global flood, and the lake dried up, and there you go. There's your explanation. It would only produce 66 feet. The rivers are going to contribute 12 feet. So we've got 78 feet, and yet we have 2,000 feet, and that's just the solid salt at the bottom of all the sediments. Doesn't include another, I've been saying in some of these other series around, because when we looked at the Dead Sea cores, and you start looking through there at the salt segments that are in there, this could be more like, 6,000 feet overall of salt that's stacked up underneath the Dead Sea out of sometimes about the max of 20,000 total feet of sediment. You also have hundreds and hundreds of feet of gypsum as well. All right. And then you have aragonite and you have all these other precipitates. So when you put it all together, precipitated minerals that have come out of the waters of the Dead Sea, overall, probably 10,000 feet of precipitated material. That all has to come out of the water somehow. So we're talking about filling it 30 times, all right? 30 times to get 2,000 feet. Then to get 10,000 feet, you're going to have to fill it 5 times more than that, right? So 150 times you're going to have to fill up the entire basin and dry it out completely. And each time that's going to take 400 or 500 years. The time is starting to add up here to some pretty big numbers. I just threw this up here so you could see the difference between halite and gypsum. Gypsum is calcium sulfate dehydrate. And that forms under moderate evaporation, or when there's intermittent freshwater influx into a fairly saline environment. And so that's occurring before the halite forms, which is when it's like really dense. All right, I think I covered all of this already. This is just a summary again of the situation we're at right now. But we have a couple more things we need to do. So what's the key takeaways from this part? We've calculated the halite deposition is vastly lower than the observed deposits. That challenges the young Earth timeline. We have layered halite and gypsum deposits. So above this 2,000 feet of salt, we have gypsum, salt, gypsum, salt, gypsum, salt, aragonite, all kinds of other stuff. We have thousands and thousands of layers, which represent fluctuating hydrological and climatic conditions over extended periods of time, meaning for hundreds of years there was greater freshwater input. And then maybe for hundreds of years, there was extreme drought, in which case you'd have much more evaporation, which causes other minerals to precipitate, right? The environment's going back and forth. We're not talking about annual fluctuations, right? We see that in the aragonite couplets, right? So there are places in the column which there are hundreds and thousands of individual couplets that look like seasons, like, dry season, wet season. But the thicker layers represent more like extended periods of time of climatic change, more dramatic climatic change. And then you also have massive sediment deposits, and somewhere you got to get these sediments in there too, and that represents more precipitation and bringing in sediments that aren't just salts. Those are falling out of the water column and forming layers on top of the precipitated minerals. Okay, given all that, right? It's like, okay, well, there's a mound of salt down there, and it doesn't look like young Earth creationists can explain the origins of that salt via the lake drying up and precipitating it, right? But okay, so how does one actually explain that? I mean, did this lake fill up 200 different times and just keep evaporating? The thing is, if it filled up 200 times, we would not expect a block of 2,000 feet of salt, which has very few layers of other stuff in it. I'm not saying it's 100% salt in that 2,000 layers. All right, I showed you pictures of Mount Sedum, and in those pictures of Mount Sedum, you saw there were like, several centimeters thick layers of pure rock salt, and there'd be like a little thin layer of like sediment there, representing a storm or something where there was sediments that were brought into the lake that settled out, and then the salt continued to pile on top, right? But it's mostly salt. However, if the lake, all right, if this big basin was filled with sediments and there's, lots of water's coming in, it's going to bring lots of sediment, and that sediment's going to fall out and form lots of layers of different sediments, right? Shales and so forth, and clays. And then as the lake begins to dry down, it's going to reach the point where salts begin to precipitate out. Well, gypsum and then salts and so forth, right? And they're going to pile up. But then when the lake fills up again, you're going to get more sediments on top. Right. So you would expect if the lake filled up 150 times, you're going to have these huge iterations of different types of sediments that would be really obvious. So the 2,000 feet, right? The 2,000 solid feet of salt needs to be explained by something else other than just like a complete filling and, evaporation events. And that's where I'm going to come back. We're going to go back and I'm going to re-emphasize this sort of the ancient history of the Dead Sea Basin. So in the conventional way of thinking, the geologists have studied this region for a long time, and they've come up with this theory about the stages of the evolution of the Dead Sea. And I showed you earlier evidence that the Dead Sea was connected to the Mediterranean Sea at one point. All right, there's a valley here that contains incores there, evidence that there was a valley there that was a conduit, all right, of water from the Mediterranean Sea into the Sodom Lagoon. And it's called a lagoon because in the conventional understanding of the history of the Dead Sea, when the plates began to slide and pull apart somewhat, this thing didn't fall into a deep basin immediately, right? A basin starts to form, but it's fairly shallow. And so you end up with this long, skinny lake, right, which is quite shallow. And so water is coming in here, and once it's in this shallow basin, it evaporates, right? It is 100 degrees. There is low humidity, right? And there's also, there's not mountains around it at this time. That's something I might have neglected to say before, but in the past, this was a much flatter area because you haven't had the uplift yet. Part of the basin formation is that as these plates are moving apart and there's upwelling that's splitting this area, that's pushing this land up, which is why it's a plateau, not really mountains, right? It's actually a plateau that's being pushed up higher and higher above sea level. So at one point, it wasn't nearly as high, in which case there really isn't much water flowing into this basin. All right. Most of the water is just like, this is gently rising all the way to this point. So water is flowing into the Mediterranean Sea. And so very little water is being input from around here. It's mostly water from the Mediterranean Sea, which is just seawater. So seawater is flowing in here. It's hot. It's dry. Water is evaporating. It's super salty, right? Because the water isn't going back. It's just constantly coming in, right? It keeps coming in from Mediterranean Sea, drying out. What's left? Salt. It reaches the level that salt precipitates. Salt begins to form crusts underneath the sea, and it just starts piling up. And it's just a conveyor belt, right? The water just keeps coming in. The water keeps coming in. The water keeps coming in. Now, we do think that during like past ice ages, not the most recent one, ice ages from long, long ago, when the Mediterranean Sea shrunk, right, and the whole ocean went down, it would have separated this valley, which is extremely shallow, from this basin. In which case, this basin was just stuck and it didn't have any source of water, in which case it dried all the way down, right? Left a whole big thick layer of salt. And then as it filled up again, it would have brought more sediments in there. So there's a little bit of layers of sediments there. And then the salt production begins again. And so this turned off and it turned on, and it turned off and it turned on, and it turned off and it turned on. But for thousands and thousands of years, it's collecting salt, and then maybe it gets turned off for hundreds of years or even 1,000 years. And then it gets turned back on for thousands and thousands of years, right? And it's just building up salt this whole time. And eventually the whole thing gets disconnected. And now, of course, it's completely disconnected today. And since it got disconnected, of course, it's too dry. And so the whole lake has been shriveling up. Sometimes it's been wetter, sometimes it's been drier. And we did a whole video on showing how Lake Lasan has gone up and it's gone down. It's gone up and it's gone down because the climate changes that have occurred in the past. But for the last 10,000 years, it's been really low, right? For the last 10,000 years, there's been a Sea of Galilee, there's been a Jordan River, and there's been a salt sea at the bottom of the valley. All right, so I actually just described most of what's on this particular slide. Yes, I explained all of that. All right, so this is all the accumulation process. So I want to go back to this particular figure that I made, my little cartoon of the history of the Dead Sea. Because before I showed you a cross-section of what it looks like today, because I was showing you like the Miocene rock, right, which is up to about like 20 million years old. The Miocene rock was like way down here at 5 kilometers below the other surface rocks on either side of the valley. All right, so 15,000 feet or more below. But in the past, right, way back in the Pliocene, which is when, this is like 5 to 15 million years ago, this is when the lagoon existed. The lagoon is much more shallow and the Miocene rocks have not fallen down as much, but this whole time it's falling down. As it falls down, the salt piles up. The land falls down and the salt piles up. The land falls down, the salt keeps piling up, right? So, the whole valley doesn't drop down 15,000 feet. The rocks all fall down that far, but the sediments keep building up. And so it is below sea level, right? So it's falling faster than it's filling, but it hasn't fallen so fast at any one time. There's been a 3,000, 4,000 foot drop all the way down below sea level. But this whole segment basically was just filled with salt. That's your 2,000 feet of salt. And then after this fell farther, then you had a lake form that had more sediments put into it. And eventually you end up with other sediments mixed in with the salts above that. All right, so the salt accumulation process. If you look at the column and you just look at the observations we can make, it looks like there was a calm, stable deposition situation for hundreds of thousands of years that allowed for massive halite deposition to occur. If there had been chaotic flooding, if there had been massive floods, it would have brought in a whole bunch of sediment and we would see thick layers of sediment mixed in with those salts. If there was a global flood that had just like mixed up everything and there was like tons of sediment in there, it wouldn't be that salty, right? You're not going to get pure salt at the bottom of all these layers. And with the young earth creationists, what they should predict is, if they are right, that you had the end of the flood, you had this huge valley, which somehow had cracked open, like cracked all the flood rocks open, pulled apart, and now there's like this big giant crack in the earth. What they should predict is that this muddy water and water from the rest of the continents should have flowed into that valley, bringing with it sand and mud and rocks and all kinds of debris, right? And that stuff should have fallen right to the bottom of that big crack. And then it piled up. And then you'd have a lake kind of left. And then all the heavy sediments would have fallen out, right? You would have, even the clay particles would have fallen out. And then the lake begins to dry up. And eventually it reaches really high salinity. And then eventually the salt begins to form. And where would the salt end up then? The salt would end up on the top. Yes, there's salt there at the top today, but nothing like that salt that's way down 10,000 feet below the sediments. All right, that 2,000 foot block of salt, I know I'm being repetitive, but I'm just stressing this because it's so important. That 2,000 feet of pure halite is below a bunch of sediments. And that's why this conventional model of it being a lagoon, right, and being just a shallow lake that's just constantly being fed seawater makes sense. The young earth creationist model just can't explain this salt layer. Okay, so yeah, let's skip this. We're not going to talk about all that deep sea drilling stuff. Shows all the different layers, shows different climatic conditions and so forth. There's been other fillings of the lake. All right, so I mentioned there's 2,000 feet of near pure salt. But above that, in previous episodes, I showed there's like, hey, there's like, 30 feet of salt here. There's 50 feet of salt here. There's 100 feet of salt here. Here's 60 feet of salt here. Here's like 10 feet of salt. Here's 5 feet of salt. Right? That's still a really thick layer. If I say there's 20 feet of salt, didn't I show you they have to dry down the entire basin in order to make 60 feet of salt? All right, so that's going to take hundreds of years, hundreds and hundreds of, I would say 500 years or more, really, in order to get that much salt laid down in the bottom. And that's when we have Lake Lausanne, right? It's separated, Lake Lausanne's when the Mediterranean Sea is no longer connected. And now you have fresh water coming in that's bringing salt. And the lake is drying down sometimes under very dry conditions and laying down thick layers of salt. And then more water gets added, the lake gets larger. And when it gets larger, salt production stops. But sediments are laid down, right? That's why you get these alternating layers of salts and sediments and gypsum and all these aragonite and all these other things in the column. So that is a wet, dry climatic cycle that's some of it's annual wet, dry cycles, but a lot of it is hundreds and thousands of year cycles. And some of those cycles are correlated with other cycles that we see in other locations, like the ice cores in Greenland, show patterns of thousands of years of, greater amounts of snowfall, and then thousands of years of less snowfall. And when we date those and we look in the Dead Sea, we find there's similar patterns during similar times, showing that the whole Earth is actually experiencing climatic shifts. Here's just my summary of all the salt inputs into that area and how much would be outputted if you were to dry all that water down. I'll just leave it up there if you wanted to pause and see kind of like a summary of all those things. Okay, that's enough of pause. Let's move on. So lastly, what are the implications? As if you haven't figured them out already. There isn't a single mechanism. Evaporation, there's river input, there's Mediterranean connections, right? We need multiple different things in our tool bag in order to explain the observations we make when we look at the sediment profile below the Dead Sea, right? There isn't just this is like a one-time event. All of this got laid down at one time. No, it looks like a progression of historical events. The geological evidence strongly indicates there's repeated cycles of expansion, contraction of the lakes, and then therefore expansion, contraction of salt deposition that extends over many, 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 many years. All right, so that 2,000 feet of halite, ignoring the other 4,000 feet and 10,000 feet of other sediments, that's going to require a lot more than 4,350 years. As we said before, it has to happen in just a couple hundred years, because there's no way that salt can be deposited after Abraham visits that area, because after that, the lake has never been big since then. And I showed you that the river can't possibly bring in that much salt. In other words, there cannot be that much salt brought into the Dead Sea in order to deposit thousands of feet of salt below it. There's independent dating mechanisms that also support this, right? We have radiocarbon dating of some of the top layers of the sediments. We have uranium thorium dating. We have the VARV counting of the individual couplet layers, showing there's tens of thousands of couplets representing tens of thousands of years, right? So then we also have the Mediterranean connection, and we have cycles that correspond to other geological records in other places in the world that suggest the same patterns of climate change. All right, so that leaves us with three fundamental challenges to young Earth creationists interpretations. There's the time problem. Even under ideal conditions, I tried to create the most ideal conditions possible. What we observed is that salt deposition would still take hundreds of thousands of years. There isn't any known mechanism that can speed this up. All right, how would you speed the salt deposition up into just a few centuries? I can't think of a way to do that. The purity of the deep sea salt sediments, all right, suggest a slow, steady accumulation rather than just a rapid deposition. All right. Now, I remind you that even that thick layer of 2,000 feet, I got to say it again, it has little thin layers of other things in there. So if you want to come up with a reason why like all that salt could have just been formed all together at one time, you have to explain the little layers of sediments between the salt layers, right? Very fine layers of sediment that are between thick layers of rock salt. There's a process problem, right? Young Earth creationists have to invoke, I think, extraordinary processes, right? None of the processes we know of can produce what we observe in the time frame that we're talking about, right? The salt conveyor belt mechanism, that requires, that's the Mediterranean Sea input thing, that requires really stable conditions to occur over hundreds of thousands of years, right? Consistent conditions in order to produce that halite in such thick layers. And then we have, look, the whole broader context of the geology of the area and the climate history. You've got the Dead Sea Rift development. All this time that this basin is sitting there developing sediments, the basin is also experiencing further tectonic activity. We saw the seismic history with the seismites showing that there's earthquakes, which then also tell you that there are times which earthquakes aren't happening, right? There's periods in which there's no shaking of the top sediments. The sea level has fluctuated. That's the Mediterranean Sea has fluctuated. There's regional climate changes. All these things demand long time scales, right? They all add up to lots and lots of time has passed. So it's important to think about all these pieces of evidence, not to just think about one and try to explain one piece of data. You got to explain why all these pieces of data, all seem to point to a long set of processes. Right? I think these findings reinforce the broad, deep time framework of Earth's history. And the next episode is where we're going to try to put it all together. I've already done a lot of that groundwork right here in this video. I've been trying to pull in some different threads and say you got to explain, not just the salt, you have to explain the sediments, you have to explain the seismites, you have to explain the stromatolites, you have to explain Lake Lisan and different levels of benches of old seashores, right? There are so many things that we've covered in the last 9 episodes. And so in the next episode, episode 10, we're going to look at the Dead Sea's geological challenge to young Earth creationism. And what that means is I'm just going to try to summarize all these different things and sort of put it together as here is the challenge I'm presenting to those who believe the world is only 6,000 years old and that a global flood and normal mechanisms, geological mechanisms, can actually explain and actually point to a young Earth. Remember, most young Earth creationists say the evidence points to a young Earth. They don't say that, if you look at this, it looks like the Earth is old. No, they say, if you just interpreted this evidence right, it all is young. But my challenge is to show me how this evidence makes the Earth look young. I'm waiting. I'm willing to listen. And I'm willing to talk about it. So the Dead Sea Chronicles, part 11, the Dead Sea Geological's challenge to a young Earth. That leaves us with only one episode after that. That's where I'm going to try to pull in scriptures, the Dead Sea, geology into one giant package in which I express my particular view and opinion of this. You've gotten a strong impression that I believe that the evidence points to an ancient Earth. But how do I understand an ancient Earth in the context of scriptures, which many people interpret as not pointing to an ancient Earth? What do I do with that? I need to address that for you, and I'll do that in part 12. So we've got part 11 coming up next Monday, part 12, hopefully the Monday after that, although I have a lot of work to do on that one still. It's going to be a tough one. All right. Thanks for hanging out with me. Have a great week. We'll talk to you later. Bye-bye. Thank you for watching this installment of the Dead Sea Chronology series. As we've explored today, the Dead Sea region provides fascinating insights into Earth's history and raises important questions about how we interpret both scientific evidence and scripture. If you'd like to dive deeper into this topic, I invite you to visit my blog, Naturalis Historia, at thenaturalhistorian.com, where you'll find detailed articles exploring each aspect we've covered today, including full references and additional resources. Here's the schedule for upcoming episodes in this series. Each new video builds on what we've learned today, helping us better understand how geology and questions of the Earth's and our origins intersect in this remarkable region. You can learn more about my work and background at joelduff.org. If you found this content helpful, please consider subscribing and sharing with others who might be interested in exploring these important questions about science and faith. Thank you again for watching. Blessings to you and all who are around you.